whenever you hear this, you want to forget that. With that, and I'm looking forward to the panel discussion we share in this room then. But having said so, with that, I want to hand over to my friend Stefan Fischer, who's talking about distributed agents. So pretty much continuing that story.
Yes, absolutely. Actually, many of you who were here last year remember that I talked about DNA-based nano networks. So obviously, this is something completely different. Since last year, and many of you already know that I'm the computer networks distributed systems guy at our university. So when you have to do something with AI in your university as a professor, and everybody has to do that obviously, then it's something like distributed AI or so in my case. And after that summer school last year, I created with my team a new lecture which is called Distributed AI. And part of it is distributed agents, just following the motto. I don't know much about that, so let's do a lecture about it. Yeah, so that's a normal trick of professors. So this is more a tutorial of how distributed agents work, why we use them, why it makes sense to at least in many situations, have teams of agents, teams of distributed agents, and how they work, basic technologies especially. But in the end, I couldn't resist and add a little research to the talk, and then we come back to the DNA-based nano networks because I try to connect these. So the talk will be first motivation example, then we briefly talk about a few architectures of which are used for distributed agent systems, the platforms that Albert just mentioned, they implement this already. And then I'll very briefly talk about two very important technical foundations, and I guess most of you have heard at least of MCP, Model Context Protocol, but maybe also of A2A, which is not that popular yet, but will probably become the agent-to-agent protocol. And then, in the end, a few words on the broader application context in edge cloud architectures, and I will talk about two MCP, well, let's say, applications, modifications that we've come up with. So first, motivation, and I can basically skip this slide because Albrecht already mentioned that. So we talk about agents, autonomous, goal-driven entities, which can be saw that exactly the same way, especially also this morning, plan, decide, act, and learn. Today, often built on large language models. We talked about agents this morning, and well, basically one important thing has changed, and that's the large language models. And since then, everybody's talking about agents and using them and so on. So, agentic AI, a slightly different definition from my point of view, would be LLM-driven agents that plan, and that's the important thing I think that makes them so popular. Plan in natural language. Call tools and APIs, that's what we have to address a little later, use memory, evaluation context, we heard about that, and are especially able to adapt to messy open world tasks, and open world is also one of the important aspects here. Let's skip that. So, but why distributed? So far, and most of us, I guess, are still more or less using agentic AI. We talk to ChatGPT and others. Well, usually we don't have really the impression that we talk to teams of agents or something. We just talk to one instance of a large language model. But why could it make sense to distribute agents? So split up the task that we have into several components and have these components executed, have the tasks worked on by different agents. Well. First, obviously, scale and parallelism, that's always what distributed systems people say. But one thing which has become, at least in the context that we are looking at these things, you know, Lübeck is a medical university, and we deal a lot with medical people and access to research data and data on patients and so on. And this is not simple. Yeah? Access to medical data and using medical data is really still a problem. One solution that people have in mind is federated learning and use data locality. So run the agents where the data is and not move the data to the agents. So one idea would be to split this task away from the overall task to the the data analysis in a specific location by one agent, and then just give the result back to the let's say supervising agent. There are several other reasons. One could be, for instance, cost issues. You all know that some of the large language models are very expensive, some others are free to use, and so there might be tasks where it makes a lot of sense to put full power on and run the high-level models of OpenAI and so on. And for us, it would be completely sufficient to have an, let's say, Olama model that you run on your own server and make use of that one. So lots of ways of how you could make use of different LLMs and different geographic locations and different functionalized specialized roles. We are currently executing a little project, a medical project, which where the idea is to create a team of doctors, doctor agents, medical agents, with a human in the loop and several other agents who have specific roles. And you can imagine that there's lots of interesting questions where we have to also, during the project, have to take humans into the loop. For instance, we have a medical doctor in our team who provides us with medical data, with patient records anonymized and everything, and then giving them to the team, and later on analyze whether if the results that are provided by the diagnostic team, if they are really good and valuable and so on, and if they are precise enough and so on. And we also have a legal guy who analyzes with us what are the possibilities of using medical data of patients and where to use them and how to integrate them and so on. So that's a typical, let's say, would be a typical application, and the team could look like this here. So you have, in a big doctor's team, let's say in a hospital, where there might be, let's say, university hospital, where you have critical and difficult cases. You have quite a few people who are involved in a diagnosis, and this is just the idea to map this on a team of agents. Now the question is, I don't want to go into details here, that's not too interesting. We don't want to learn about how doctors work and what doctors do, but I think you can all imagine what the idea is. Now, how could we organize the teamwork among the agents? So what are the architectures, the topologies that we can use for the cooperation? But there's a few in what I wanted to say, Albrecht, when you said, well, there are still 50% better with AI, but you also have to keep in mind that AI is only 3 years old and not 25. So maybe it learns a lot more. Anyway, as distributed systems people, we immediately came up with some nice architectures of how cooperation of agents could work. So one, let's say, interesting one is the blackboard architecture. So you have a blackboard in the middle of all agents, and all agents provide their results and get results provide their results, write them on the blackboard, and read stuff that is interesting for them. Good for coordinated problem solvers, but obviously it uses asynchronous communication, which probably delays the production of results a bit. Another option, peer-to-peer architecture, quite popular also in distributed computing, that could lead to, has advantages like high fault tolerance, for instance, and enables real-time decision-making because they synchronously communicate with each other, but on the other hand it requires rather complex routing and synchronization among the agents. So if every agent here has to communicate with 5 other or 6 or 7 other agents, it becomes a complicated situation for every agent. So the architecture that is, as far as I could tell, is most popular today is the let's say some master-slave or master-worker version. So you have a master that's typically the agent who talks to the let's say to the human or to whatever the prompter is. So who talks to the human, and then the master has the job of splitting up the task and maybe even finding the right agents here. Yeah, so it doesn't even have to be the task of, let's say, the human or the system designer to find the right set of agents. It might even be possible that the master here does that job first. Yeah, to assemble his or her or its team, like a planner, analyzer, optimizer, and so on. So that's I think that's the one that is usually used today, at least in most multi-agent applications. And service-oriented architectures, certainly also. That's maybe not so much meant for the communication between agents, but it's meant for providing agent with more information of what is around the agent. So access to sensors, for instance, to files, to databases, and so on. And this immediately brings us to the, both bring us immediately to the two technologies that are central for distributed agent architectures. So let's skip that one here. The first one is Model Context Protocol. The idea, more or less, is, and this, MCP is, I would say, is just the current outcome of what of discussions that have already started, at least more or less right after the beginning of when LLMs became popular. So because what happens if you publish an LLM, well, then the LLM is as it is, and it basically knows the version of the world that it learned until that time when it was published. So the question is, how is it still possible that agents are able to tell us something about the current reality, about, let's say, that tonight there's the World Championship soccer match between Germany and Paraguay or something like that. How is this possible? And in the early times it wasn't. But since quite a while, the big companies and also universities started to develop solutions for that. The first solution that was used for that was called function tools, and you can still use that and still very popular. Function tools basically means you have you can create simple library functions that you can then use to access the environment, like doing web calls, web searches, and things like that. MCP is more or less just a way of standardizing this. Yeah? So MCP is the new standardized version of what used to be function calls. And the idea in functions calls, you had a local library. You use the library, let's say, in your Python programs. But when you wanted to use the same services in another program, then you had to copy the library to the other guy who wanted to use it instead of using it centrally. And MCP is the idea of using that in a centralized way. Yeah? So we have an MCP server, or we have several MCP servers connected to MCP clients. The MCP host is more or less the LLM-based system. Yeah? So this would be the agent here, which has typically several MCP clients, and these clients then get access to MCP servers, which provide access to different contexts like databases, APIs, files, and so on. Yeah, that's and I mean, for distributed systems people, this is not really a surprise. Yeah, you would build systems like this, more or less. Not too much detail, but that's the typical workflow. You first do discovery of tools. Dear server, what do you offer? Then you get a list of tools, the LLM selects tools depending, and you don't have to tell the LLM, please select the following tools, but what do? You describe the way of, or the service that is offered by MCP, you describe this in natural language. And LLMs learn or read, let's put it that way, read the service description, and then they know what to expect from the service and simply use it. Whenever they think that this service would be useful, they call it. Yeah, and then start this invocation, call the cool, get tools, get a result, and then process the result. And well, there's more like updates and so on. Yeah, that's the idea of MCP, just very quickly. Second important component of distributed agent systems is the agent-to-agent protocol, A2A. Basically, when you want to build multi-agent scenarios today, there are two options. The first option is already a bit older. So if you look at platforms like Crew AI, very popular, and LangChain and so on, they do it usually like that. Yeah? So you have more or less one process, and you have several agents, and the agents communicate with each other, typically via standard I/O, sometimes by HTTP. Then it might even be several processes, but they are all living in the same ecosystem, running on the same platform. Yeah? So you program an agent system which is not really distributed, but at least it consists of several agents which communicate with each other. The new one, and this is quite obviously that we had to come up with that, is more the heterogeneous distributed way. So we distribute our agents over different servers, over different locations, and they might even live in different ecosystems. So this could be LangChain, this could be the Google, that could be the OpenAI platform, and then they can still communicate with each other because, well, we have developed this heterogeneous protocol, the agent-to-agent protocol, which is implemented in order to allow for the communication. And this is not really old, introduced by Google only a little more than a year ago, yeah, so still very, very new, designed exactly for this purpose. Interestingly, hosted now by the Linux Foundations as an open source project. Why? There were actually two competing proposals. That was the agent, I think I have the APC or ACP or something. I think it's ACP. At least it's a protocol like the A2A protocol. Basically, does exactly the same, but developed by different consortium and developed in parallel. When Google made the step to make its protocol open and public and available through the Linux Foundation, the other group stopped the development of their project and joined forces with the Google group. So now everyone is developing the A2A protocol, which makes a lot of sense in my eyes. So an open protocol which everyone can use and further develop. The block diagram looks basically the same. So we have the user here who has access to an A2A client, and the A2A client then calls or has the chance or the possibility to communicate with A2A servers and find out what agents are running there, what can they do, can they do the purpose that I need them for, and so on. This is a typical communication between client agent and client server. So here the client agent here. The client agent would be able to send tasks to the remote agent. So tell the remote agent, please do the following thing for me. And then there could be a rather complex protocol, like for instance, the remote agent could ask for more information, which could be returned. Then it could even send asynchronous updates, and then finally send a final response and an artifact while it processes this task. And it can even get in touch with other agents, certainly. Yeah? So another rather complex protocol. And these are the components basic components that you would need in order to set up a distributed agent team. And obviously, as usual, there are libraries for that, and you don't have to. You don't have, when you start developing, you don't have to know much about the internals. As a developer, you don't see much of the JSON that is used in the background, but you can just use the library functions, and at least in most of the platforms, it has already become very convenient to create teams of agents with that. Okay, let me, at the end, 5 minutes, Christian, give you a broader application context in edge cloud architectures. So what could you do with that? How could systems look like that especially use DNA-based nano networks? So we have seen similar images like this this morning and later, and so everybody is obviously talking about cloud and fog and edge and so on. There's one slight difference here. Here we are looking not at the edge, but we have added the extreme edge. Yeah, what is extreme edge? We call everything that is, especially if we call extreme edge AI. We talk about networks, neural networks, which are not in silicon, which are not silicon-based networks. So they are not implemented on a computer, but they are natural physical networks. And one example, you might have guessed that, molecular DNA-based nano networks. So since last year, we've been in my group. We have begun working on using, you might remember this DNA tile technology. We have started using this DNA tile technology to create physical neural networks within, let's say, first in petri dishes in our vision, but more or less in the human blood, yeah, in 50 years or so. And we call this project Smart Blood. Yeah? So we have clever DNA-based neural networks which are implemented in the blood and which can measure certain parameters and so on. The question now is how can we make this information here available to the outside, and how can we make it use, and how can we make the outside start this? Sounds, again, I know that sounds very, let's say, visionary and crazy, but actually there's at least 9 different ways of how to create 9 different classes of creating physical neural networks. DNA-based neural networking is one of them, and it's not that we invented that. People have been working with that for 15 years now. Yeah? So if you look at the literature, there's work on DNA, using DNA for creating neural networks since 15 years. Yeah? So not really new, but the idea of how can we really implement this, and can we make it usable in edge cloud AI systems, that becomes more and more interesting and becomes more and more, let's say, solvable. There's lots of other different technologies for physical neural networks. What we came up with is more or less, let's say, something like an adapter between the MCP that we know that makes services available to agents and so on. We have an adapter physical MCP which allows to access different kinds of physical neural networks, which are actually much different from in silicon networks. For instance, for all kinds of chemical networks, you have to start the networks in the sense that you have to supply certain molecules in order to start the whole process. And when the network has come to a conclusion and you want to restart it again, it's not simple. You first remove the results from the medium and have to fill in the new materials and so on. Yeah? So much completely different from normal in silicon neural networks. So we are working on this on physical MCP, and a second example. And actually this is a physical neural networks as a biological computer, which you can really buy already, and which fortunately you could also get access as a cloud access as an API. If you want to use that, you don't have to buy that for a few €100,000. You can get monthly access for, I think, something like €2,500. So it's still very much, but maybe within a project doable. Second thing that we do. Who has heard of SDC? SDC is a protocol which has been developed in around 2015. And it's becoming more and more popular. It's in terms of economy and business, becoming more and more important. It's a protocol to connect medical devices heterogeneously. Yeah? So this is not standard. We can connect all typical devices which we use for our purposes here and for music and so on. But in medical technologies, this is not usual. So when at least it wasn't usual, let's put it that way. When you buy a Siemens devices, it's very hard to connect them to, let's say, Träger or other devices. And SDC is a protocol to take a step in this direction towards heterogeneous connection. And the question now is, can we also use this in agentic AI? And then the simple answer is, well, let's try to create a gateway between the SDC world, which describes and connects all these devices here, so all medical devices, let's say in operation room, and then make this available to LLM-based agents by MCP. Yeah? So giving them access to that, and the final result could be something like this. And again, this is now really rather visionary, but we have a doctor who talks to his team of agents, agent or teams of agents, which has all these MCP services, for instance, our physical MCP or the SDC gateway, and then, for instance, get access to maybe not situations like this. Maybe this is still a bit overdone, but getting access to, let's say, body parameters of people who are then provided by the gateways and interfaces that are offered by this human here. I know you look like last year, but well, we'll see if this how long it takes until people really talk about this. With this image, I'm done, I think.
Thank you, Stefan. We're lagging already a bit behind, so while we change computers, there might be time for a quick question. Boris.
Yeah, thank you very much for the very comprehensive presentation. I was just, because I have not worked with MCP, but I know about it, and I was just asking myself, if you have distributed agents, usually you have some, let's say, degree of local decision making that you have, and you would also have to know, let's say, what is the potential quality that a remote service can give you. I just wanted to ask, do you know, like, what are the common decision making mechanisms if you know, okay, can you do this locally? Do you need to offload this task, for example, to another agent? Is there existing sophisticated mechanisms for this?
I don't know in detail, but I mean, there are obvious tasks which you cannot solve without within the LLM agent, which the agent finds out that it cannot do that, and then it needs other sources. But in principle, you're right. I mean, in terms of there might be different ways of solving a certain task, and the question which of the available, let's say, sources, external sources to use. I don't know actually if this is implemented within the MCP environment or within LLMs. At least, I mean, you can, as a designer of the system, you can at least make sure that your agents only get in touch with MCP servers that you trust, for instance. Yeah? So you don't let the agent search for their own MCP, at least not yet. You never know. So you have to say these are the MCP servers which are available. Yeah? And there are, I mean, there are also, let's say, curated MCP servers that you can find and that you can, as a designer, look at if this is what you need. But let's say deciding what to use, I don't know.
Okay, thank you so much for your questions and the talk. I hand over to Aaron talking about the dilemma of